Hi, here is a nice proof regarding convergence and divergence of the series. In today's video, we are going to see something is called the root test. Okay, in order to determine this series is a convergent or divergent, is enough to calculate this limit, a root of n of a sub n equal to L. If this L is strictly inferior than 1, this series is automatically going to be converged. If we have L strictly superior than 1, this series is going to be divergent. If you have L equal to 1, this series doesn't provide any information. Okay, so we have to change another test. Okay, so now we are going to prove the case of L strictly inferior than 1. Okay, in order to get this series converged. Okay, so now let's prove this one. Let's take this case, the case of this L strictly inferior than R, strictly inferior than 1. Okay, there exists R between L and 1. Okay, such as R is superior than L. So this one, we already have this limit. In order to have this limit as strictly inferior than 1, we have this limit as n goes to infinity. This limit of a sub n, absolute value of a sub n, equal to L, which is strictly inferior than 1. This implies this a sub n, absolute value of a sub, the root n of this absolute value of a sub n strictly inferior than R. Okay, it's equivalent. I'm going to raise n power on both sides, so I will have absolute value of e sub n strictly inferior than R to the n. Okay, so now we have absolute value of e sub n strictly inferior than R to the n. We have this one, we have this absolute value of e sub n strictly inferior than R to the n. Okay, so I'm going to apply the sum notation on both sides. So before we do that, there is sum capital N such that n superior or equal to capital N. Okay, I'm going to apply the sum notation on both sides. So we'll have the sum of a sub n as n, it goes from capital N to infinity, a sub n strictly inferior than the sum of R to the n as n goes from capital N to plus infinity. Okay, so as you know here, this is the geometry series as a convergence series because we have absolute value of R strictly inferior than 1, as we mentioned before here. So this one is converged series. So by comparison test, this series is going to be converged as well. Okay, so I'm going to do the whole sum of a sub n absolute value as n goes from 1 to plus infinity equal to this partial sums of a sub absolute value of a sub n as n goes from 1 to capital N minus 1 plus this partial sum of a sub n as n goes from capital N to plus infinity. Okay, now as we proved before, this one is a convergence series. This one already proved this one is a convergence series because we have used the comparison test. This one is a finite sum. That means it converged because it's going from 1 to capital N minus 1. So finally, thus this sum of a sub n as n goes from 1 to plus infinity is absolutely converged. Implies finally this sum of a sub n as n goes from 1 to infinity converges. Okay, let's move on to the next case. Now I'm moving on to the next case, the case of when we have L strictly superior than 1. Okay, we are going to do the same thing. So we have as L strictly superior than R strictly superior than 1. Okay, so now as we have here the limit of the root n of a sub n as n goes to infinity equal to L strictly superior than 1 equivalent root n of absolute value of a sub n strictly superior than R, okay? R strictly superior than 1, okay? This one is equivalent absolute value of e sub n. I'm going to raise the n exponent on both sides, so I will have e sub n absolute value of e sub n strictly superior than R to the n. So equivalent, I'm going to apply the sum notation on both sides, so I will have the sum of a absolute value of e sub n as n goes from 1 to infinity strictly superior than sum of R to the n as n goes from 1 to plus infinity, okay? R strictly superior than 1. So there is sum capital N such that n superior or equal to capital N, okay? Such that the sum of e sub n, absolute value of e sub n as n goes from capital N to plus infinity strictly superior than the sum of R to the n as n goes from capital N to plus infinity. As we know, this is geometry series as a divergence series because we have R strictly superior than 1. So this one by comparison test, as you see here, this is geometry series as a divergence series because we have R strictly superior than 1. This is diverge. By comparison test, since this one is bigger than this one, since this sum is bigger than this sum, that means this sum is a diverge as well. This sum diverge sum as well. So the sum of absolute value of e sub n as n goes from 1 to plus infinity, this one equal to the partial sums of the sum of a sub absolute value of e sub n as n goes from 1 to capital N minus 1 plus another sum of absolute value of e sub n as n goes from capital N to plus infinity, okay? So we already proved this sum is a divergent sum because of comparison test. This one is a finite sum, is a convergent. But when we have two sums, one is divergent, the other one is converged, equal to the diverged sum. This one as a whole sum is arithmetically diverged, okay? So now I'm moving on to an example to support this proof, okay? Now I'm taking this example, we have this sum. So now I'm going to check this, I'm going to calculate the root test of this sum to check this sum is converged or diverged, okay? So it's enough to calculate the limit of the root n of this sum absolute value of n. This one equal to the limit n to the n over 3 to the 1 plus 2 1 over n, okay? As n goes to infinity. So this one equal to n over 3 1 over n plus 2 to the n to this one 1 over n. So this n is going to be cancelled out with 1 over n. So I will have over 3 1 over n plus 2, okay? So I'm going to calculate, I'm going to apply the limit of this one. So the limit as n goes to infinity, okay? This one equal to n. If I'm applying the limit of 1 over n, is giving us 0, 3 to the 0 equal to 1. So 3, I will be left with 3 to the 2. So you apply the limit here, this one is going to infinity. Finally, this sum diverges here, okay? So I have done with this problem. Just consider the subscribes. Thank you for watching. I will see you in next video. Bye.